Hi everyone, welcome to lecture 19, which is the first lecture we'll see on the probability calculus. The objectives for this video are the following. After watching, everyone should be able to, number one, define the probability calculus rules for tautologies, contradictions, mutually exclusive statements, and logically equivalent statements. And number two, prove the probability calculus rule for negations. And number three, prove the probability calculus rule for general disjunctions. So this week we'll be starting the probability calculus. The topic is going to take us 2 weeks to look at in full depth. And so far we've been using the word probability a lot. We've said things like inductive probability, epistemic probability, but we've been using the term freely without any kind of precise definition of what a probability exactly is. So over this week and next, we'll look at the mathematical rules that a quantity must satisfy in order to be properly called a probability. As a result, this week and next week will be more focused on the math rather than the philosophy. So I just said we've looked at two different types of probability so far. These two. We've seen inductive probability, which we said applies to arguments, and we've seen epistemic probability, which we said applies to statements. Now, there is a third type of probability, one that applies to properties. And this type of probability is what we're using when we speak of things like the probability of throwing a 2 on a die. Now, all three of these types of probability obey the rules of the mathematical theory that we're about to develop. So this theory applies to all the concepts of probability that we've seen so far. And when we develop it, we will develop the probability calculus as it applies to statements. So for example, we'll be speaking often in terms of things like the probability that you get a 6 on a die rather than the probability of some property being present. Now, we've seen truth tables for statements way back in the beginning. We saw the truth tables for not, and or. The truth tables we saw told us whether a complex statement is true or false, and how this truth or falsity depends on the truth or falsity of the simple constituents of that complex statement. Now, in a similar way, the rules of the probability calculus tell us how the probability of a complex statement is related to the probability of its simple constituents. The probability calculus, notice, does not tell us what the probabilities of those simple constituents are. That's a problem for inductive logic. But given the probabilities of simple statements, the probability calculus tells us how we calculate the probability of complex statements that are built from those simple constituents. So let's take a look at some of the rules of the probability calculus. A bit of basic information before we look at the rules themselves. Probability values assigned to statements range from 0 to 1, so they are numbers. And if P is a statement with probability 1/2, we write this, which we read as P of P is a half, to indicate that P is a statement with probability 1/2. Now, we've seen various special kinds of statements over the course of this class so far. One of the kinds we've seen are tautologies, which are statements that are true in every row of their truth table, or true no matter what the facts are, or true no matter what. Now, since a tautology is guaranteed to be true no matter what, we make the following definition. If a statement P is a tautology, then P of P equals 1. Notice that usually in a definition I put the thing we're defining in italics. Now, the thing we're defining here is the probability of P, which is in math speak on the slide. So that's why here there's no italicized word, but that's what we're defining. We're defining P of P here. Now, just as we've seen tautologies, we've also seen contradictions, which are statements that are false in every row of their truth table, or false no matter what the facts are, or false no matter what. Now, since a contradiction is guaranteed to be false no matter what, we make the following definition. If a statement P is a contradiction, then P of P equals 0. Another term we've used for statements of a certain kind is logically equivalent. Now, two statements, remember, are logically equivalent if they agree in all rows of their truth tables, or when they are true in exactly the same circumstances. So if a certain statement makes a claim that has a certain probability, we should want a logically equivalent statement to have the same probability. So in light of that, we make the following third definition. If two statements P and Q are logically equivalent, then P of P equals P of Q. Good, so we've got three basic definitions on the table already. Now, just as we looked at the truth tables for negations, disjunctions, and conjunctions, the next thing we'll look at is the probability rules for negations, disjunctions, and conjunctions. We'll cover the rules for negation and disjunction in this video. First, let's look at the disjunction of two statements. Now, another term we've used to describe certain kinds of statements is mutually exclusive. And two statements are mutually exclusive, remember, if they cannot both be true simultaneously. Now, using this idea, we make the following definition for the special case of disjunctions of mutually exclusive statements. We say if P and Q are mutually exclusive statements, then P of P or Q equals P of P plus P of Q. Now, the intuition behind this is that P and Q cannot be true at the same time. So to calculate the probability that at most one is true, you can just add the probabilities of either one of them being true. Okay, so these are the four basic definitions we'll see in this video. So let's get an example on the table and get a better flavor of how they work. So suppose we have a single six-sided fair die with sides numbered from 1 to 6. Then the probabilities of any individual number coming up when we roll the die are these. So all of them are 1/6. Now suppose we're interested in the probability of either a 1 or a 3 coming up. And we know that the statements a 1 is rolled and a 3 is rolled are mutually exclusive. We cannot both have a 3 and a 1 rolled after a single roll of the die. So, to calculate this probability, the probability that we roll a 1 or a 3, we apply definition 4 because that concerned the disjunction of two mutually exclusive statements, which is what we're dealing with here. And using definition 4, we see that P of 1 or 3 is rolled equals P of 1 is rolled plus P of 3 is rolled, which is 1/6 plus 1/6, which simplifies to 1/3. Okay, so this was a simple example that shows how the definitions get applied, and in particular it showed how the special version of the rules for disjunction gets applied. It applies when the statements in question are mutually exclusive. Now, before we go on to derive the general disjunction rule, which applies to the disjunction of any pair of statements, whether they are mutually exclusive or not, we actually have enough definitions on the table at this point to prove the rule concerning the probability of negations. Now notice that this isn't us making a definition. We're going to work from the definitions we already have and derive or prove the rule that we're interested in. So let's deal with negation before we get to the general disjunction rule, and I'll walk us through how to do that with a bit of interaction on your end too. So let P be a statement. We're interested in expressing what P of not P is in terms of P of P. So consider this statement, P or not P. Now here's a question about that statement, P or not P. Okay, we should have that they are mutually exclusive. P and not P cannot both be true at the same time. This follows from the truth tables for P and for its negation. So we've got a pair of mutually exclusive statements, so we can invoke definition 4 from earlier. So here is another question. We should have P of P or not P equals P of P plus P of not P. They're mutually exclusive, so we just add their probabilities. Now we can see we've got P of not P in an equation, and that's the thing that we're interested in deriving an expression for, so we know that we're getting somewhere. So here is the next question. So we should have that P or not P is a tautology. It's true no matter what. and this again can be checked using truth tables. So now we've got a tautology on the table, so we can invoke definition 1 from earlier. So here is the next question. We should have 1, which follows straight from definition 1. Probability of any tautology is 1. So on one hand, what have we got? We've got P of P or not P equals P of P plus P of not P. And on the other hand, we've got P of P or not P equals 1. So, putting those two results together, we get P of P plus P of not P equals 1. And when we rearrange that, we obtain the following proposition, which we've just proved using the reasoning we've just been through. Proposition 1, if P is a statement, then P of not P equals 1 minus P of P. And this is the negation rule, which tells us how to calculate the probability of the negation of a statement using the probability of its simple constituent, the statement itself. So let's have a look at another example. Here's proposition 1 again. This is the rule we've just proved. And suppose we're rolling our die again, and we want to know the probability of not getting a 6, which is P of I do not roll a 6. Then, using the probabilities from before and the proposition we just proved, we can straightforwardly calculate P of not 6 equals 1 minus P of 6, because the statement I do not roll a 6 is the negation of the statement I roll a 6, and this is 1 minus 1/6, which is 5/6. So again, another simple example that just shows how this rule gets applied. So we've got negation on the table, and we've got one special disjunction rule that applies when two statements are mutually exclusive. That was definition 4, remember? The last rule we'll look at in this video is the one that treats the disjunction of any pair of statements, not just mutually exclusive ones. Just like the negation rule, this rule is something we can prove using the definitions and the proposition that we have on the table so far. So to do this, we're going to make some clever choices of statements that we know how to calculate the probability of with what we have so far. So consider the three statements P and Q, P and not Q, and not P and Q. Now it's a fact that all three of these statements considered together are mutually exclusive. Now what do I mean by this? Notice that our definition of mutual exclusivity treated pairs of statements, so just two, but the definition works for any finite number of statements bigger than 2. We just say that n complex statements, where n is a finite number greater than or equal to 2, are mutually exclusive just in case they cannot all be true at the same time. So these three statements cannot all be true at the same time. This is something that you'll be checking using truth tables on the assignments so that you can fill in the missing details of this proof yourself. Now, since the three statements there are mutually exclusive, we can invoke definition 4 again, or a generalized version of it, so that we can treat more than two statements and say that P of P and Q, or P and not Q, or not P and Q, is equal to P of P and Q plus P of P and not Q plus P of not P and Q. Remember, we're just adding the separate probabilities of each disjunction in that big complex statement there. Now, since the three statements cannot all be true together, it follows that no two of those statements can be true at the same time either. Any two of those statements are also mutually exclusive. So using this fact, we can write down two more pieces of information in addition to the red one that we've got down there. The first one is this: P of P and Q, or P and not Q, is equal to P of P and Q plus P of P and not Q. And the third one, which we'll write in blue, says P of P and Q, or not P and Q, is equal to P of P and Q plus P of not P and Q. All we've done there is apply the special disjunction rule to 2 out of those 3 statements to get each piece of information, numbers 2 and 3 down there in green and blue. Now we look at what we've got, these three equations, 1, 2 and 3, in red, green and blue down there. The next thing we need to spot is that we know something about the complex statements in the left-hand side of each of those equations. So let's look at the second one first, in green. We know something about the complex statement P and Q, or P and not Q. And we know, in fact, that P and Q, or P and not Q, is logically equivalent to the simple statement P. And this, again, is something to check using truth tables. So we can invoke definition 3, which treated logically equivalent statements. And by definition 3, we know that the probability of the first statement, so P of P and Q, or P and not Q, is equal to the probability of the second statement, so P of P. So this I've labelled equation 4. Now if we put equations 2 and 4 together, we get equation 7 down here, which says P of P equals P of P and Q plus P of P and not Q. So this is the first step of this next stage of the proof, and now we're going to do something entirely similar to the blue and red equations. So next, look at equation 3 in blue. The next thing we can spot is that we can do a similar thing. It's a fact, again, to check using truth tables, that the complex statement in the left-hand side of equation 3, P and Q or not P and Q, is logically equivalent to the simple statement Q. So, applying definition 3 again, we know that P of P and Q or not P and Q is equal to P of Q. I've labelled this equation 5 down there. And then putting equations 3 and 5, so the blue ones together, we derive equation 8, which says P of Q is equal to P of P and Q plus P of not P and Q. Now we do something similar again with equation 1, the red one that we haven't done yet. So we know something about the complex statement in the left-hand side of equation 1. We know, in fact, and again you can check this using truth tables, that P and Q, or P and not Q, or not P and Q, is logically equivalent to the complex statement P or Q. So, applying definition 3 again, we get equation 6, which says P of P and Q or P and not Q or not P and Q is equal to P of P or Q. And finally, putting equation 1 and 6 together, we derive equation 9, which says P of P or Q equals P of P and Q plus P of P and not Q plus P of not P and Q. So using equations 1, 2 and 3 and a bit of what we know so far, we established 4, 5 and 6 down there, and we put all those things together in their matching colours down there on the screen, and we've come up with these three new equations, 7, 8 and 9. Now the next thing we're going to do is add 7 and 8 to get equation 10 down here, which says P of P plus P of Q equals 2P of P and Q plus P of P and not Q plus P of not P and Q. Now, by adding the equations together, I just mean add the left-hand sides of equations 7 and 8 here, and add the right-hand sides of equations 7 and 8 here. And doing that, you'll get the left-hand side of equation 10 and the right-hand side of equation 10. That's why we've got two lots of this P of P and Q in equation 10, because it appears in both equation 7 and in equation 8, so we count it twice when we add them together. The next step is to subtract P of P and Q from both sides of equation 10. Doing this, we get equation 11, which says P of P plus P of Q minus P of P and Q, that's subtracting it from the left-hand side, equals P of P and Q plus P of P and not Q plus P of not P and Q. And there we've subtracted it from the right as well. And now if we look at what we've got, we're almost there. Look at equations 9 and 11 on the screen. And we notice that the right-hand side of equation 9 is the same as the right-hand side of equation 11. So, putting those two equations together, we know that the left-hand sides must be equal as well, because the right-hand sides are. And doing that, putting 9 and 11 together, gives us what we wanted. Proposition 2, which says for statements P and Q, the probability of P or Q, so the disjunction, is equal to P of P plus P of Q minus P of P and Q. And this is the general rule for the probability of disjunctions. Now, I'd highly recommend writing this proof out again in your own time, step by step, as we've done it here. I'm probably doing it a few times because it's one of the more complicated things we've seen so far, and I might ask you to prove things on assignments or exams as well, so this is good practice. Okay, so on the table we've got the negation and disjunction rules. Now notice that in the equation for P of P or Q in proposition 2, we also have P of P and Q on the right there, which is the probability of a conjunction, which we haven't actually looked at yet. Now that's why we won't do an example here where we apply proposition 2. Instead, we're going to wait until we've got the rule for conjunctions as well, so we can apply everything together. There's also lots of assignment questions that ask you to calculate things using these rules as well. So the important things to know are the rules, the definitions of them, where we define them. So there were 4 definitions at the start of this video, and the proofs of them, where we proved them, and we've proved 2 of them in this video. So next time we'll have a look at the conjunction rule and another thing called conditional probability in the second installment of the probability calculus. So have a go at your self-reflection question, and I'll see you all next time.